In my last lecture, I discussed about the overview of microgrid and the energy storage unit and the design means the sizing analysis of energy storage unit. And in that lecture, I told you about there is a box, black box, which is a power electronics converter, but I have not discussed anything about the power electronics converter used for this any of the component, and some of the power electronics converter is already discussed by Professor Sarkar for the source, means mini hydro power plant design and its corresponding power electronics converter is already discussed by Professor Sarkar. But in my today's lecture, I am going to discuss about the power converters that will be used for the energy storage system. So, when I am talking about the energy storage system, I will be talking about the different types, means I will just scroll down the types of the power electronics converters, but my main focus will be on the design of this power electronics converter, which will be used for this battery energy storage system basically, and its simulation. So, these two are the main focus of this today's lecture. So, I will be doing I will show you the simulation steps, and finally, I will give you the Simulink model for it. So, to start with, let us talk about the power electronics, that is converters that is going to be used for this energy storage applications. And already in my last class I have focused about this electrochemical energy storage that are being used for a standalone system. It can also be used for grid connected applications. But how to choose whether depending on if you are integrating the power electronic storage energy storage with the corresponding grid, if the grid is AC or DC, depending on that you have to choose two types of power electronics converter. That is, if you are connecting to the AC source or AC grid, then you are going to, because the storage side it is the DC fixed. So, either you are going for a AC to DC converter, or if you are integrating with a DC grid or DC microgrid, you can say microgrid, then you are going to use a DC to DC converter. So, these are the types of power electronics converter broadly we are going to use for when we are going to interface the storage energy storage system. And when I am talking about the energy storage, basically we are mainly focusing on this electrochemical storage, and where we have discussed about these two storages, that is the battery and supercapacitor, which is having the complementary characteristics. This nowadays it is mainly used for this microgrid applications, battery which is having high energy density and the supercapacitor which is having high power density because of their complementary characteristics. So, these batteries can be used for the steady state application, and for transient application we are using the supercapacitor or the ultra capacitors in the microgrid application, so that it reduces the size of the battery. So, that is the type of storage that is being used in the energy storage side. So, but apart from in between these two storages, I am not talking about the hybrid energy storage here, I am talking about only the single storage, and that too, that is the battery energy storage system. So, I am talking about the sizing of this battery I have discussed in my last lecture. So, I will talk about now the accessories or the intermediate stage which will be there as a power electronics converter, so that we can interface the storage with the grid. The grid can be AC or DC. So, and it has to operate bidirectionally. Why bidirectional operation is needed? Because when I am interfacing a energy storage to the grid, so the grid can be AC or DC, that is separate, but the bidirectional means depending on the source, if you have a excess of energy, if the generation is more, then we have to store it. So, the battery has to, or the energy storage system has to absorb the power or it has to store the power, and when there is a deficit of energy or deficit from the supply, then and load is more, so then we need to, the battery has to supply or it has to discharge. So, in that case, so we need a bidirectional operation. So, we have to choose the power converter, so that it can operate bidirectionally. So, this is the and we are mainly focusing on this microgrid or this grid applications, and I will just talk about the different types, which there may be some overlap with Professor Sarkar, but I will show you the names here. So, for the while we are going to interface the power electronics converter with AC grid or AC bus or AC microgrid, you can say anything, AC microgrid, then we need a AC to DC converter, and the types are broadly boost type, buck type, buck boost type and multi-level type. Multi-level types are has given some idea on it, and this boost, buck and buck boost type for this 3-phase AC system, when this is the grid, we are interfacing with the energy storage, which is DC. I am interfacing this. So, in between we have different topologies. So, this is the topology for a bidirectional boost. So, power flow is possible bidirectionally. Okay. The grid can supply or grid can take, or the energy storage can be charged or it can be discharged. So, we need a this bidirectional converters. So, the switch has to be operated bidirectionally. So, it must have the its body diode or the feedback means internal diode, so that it can operate bidirectionally. So, here in the bidirectional boost type, we have I have shown here 3 topologies which are available in these references. So, you can go through it. So, one is bidirectional 2-leg, first one is the bidirectional boost type 2-leg converter. So, we have 2 switching legs here. So, you can see it clearly. So, we have 2 legs here and 3-wire system, and this one, this is the topology with 3-leg 3-wire system, and this is the topology boost type, bidirectional boost type and 3-leg 4-wire system. So, these are the topologies for which are used for this AC to DC converter as the AC to DC power electronics converter, and then in the buck type there may be some other topologies also, but I have shown some topologies which are normally in use for this to interfacing this AC grid with the energy storage. So, this is the buck type topology, where you can see that there is a LC filter in the output, and so this topology is having a 3-leg as well as 4-leg structure. Okay. This is a 3-leg, it uses 3 legs, and for high power the switches can be GTOs, and for low power applications the switches can be IGBTs. So, this 4-leg topology is advantageous because it reduces the DC link voltage ripple, and also for balancing currents in case of the unbalanced supply system. I am just giving you just the overview of the AC-DC converter, bidirectional AC-DC converter that is being used, and some standard topologies. So, this is another type, that is the third one, that is a bidirectional buck boost type, where I have shown only 3-leg structure. Okay. And the fourth one is the multi-level type, where we have different topologies, again multi-level diode clamp, flying capacitor and cascaded, and obviously you know the advantages of multi-level topologies, when why and when we are going for this multi-level operation. So, when in multi-level converters, we have the advantage of better power quality, that is the lower THD, lower EMI, electromagnetic interference, and it gives better power factor or higher power factor. So, this is about the AC to DC converter topologies we are using for this for interfacing between the microgrid with the energy storage system. Then our main advantage means our goal is to talk about this DC to DC converter interface. So, we are integrating this with a DC grid, in between DC grid and the battery energy storage system. So, battery energy storage means the battery, the energy storage unit along with the power electronics converter. Power electronics converter forms this battery energy storage system. So, here also there is a overlap, that is isolated type and non isolated type, and isolated type is already greatly means in detail it is discussed by Professor Sarkar. So, and here are the applications I have mentioned, that is for the this DC to DC converter, we are integrating DC grid, and the in between the DC grid and base we are putting this power electronics interface, which is a bidirectional DC to DC converter. Before coming to the topologies used for this DC to DC converter, for the DC to DC converter, the applications are already we are discussing, that is DC microgrid means the renewable energy system integration. So, when the source is having DC and the storage is obviously DC. So, we are going for this application. Another is the interface between the again the DC link and the ESS, that is the line interactive EPS, and the most important apart from the this microgrid applications nowadays the important another factor is the EVs, which are means for EV battery charging. I am talking about the energy storage, which is used for in the microgrid for the storing the energy, and it will EV will be as a load. So, that is also used with means that is also another application where we are using this bidirectional power electronics converters. Okay. And so, this is the already today means just half an hour before you have discussed, sir has done I think simulation also. You have discussed the modulation techniques, the details of DAB, the dual active bridge converter, which is nowadays very much used for this microgrid applications. So, this already covered. So, I am not going to talk anything about it. So, now the main thing comes here, the non isolated one. The non isolated one is the between the DC grid, that is I am putting in between the DC grid and the energy storage unit. So, I am putting the this DC to DC bidirectional, that is BDC, okay, between the DC grid. And so, here the topologies which I am not going to explain, I am discussing that one first, that is the Chuk converter and the SEPIC converter, which are also used. These two converters uses two actively active switches, okay, and there are the filter all other filter components. So, components are more. The advantage is it gives low ripple input and output currents compared to the other one, but the number of components are more, and it uses two active switches. So, and also gives a high voltage conversion ratio. Okay. So, this is the advantage, whereas the main drawback of this Chuk converter and the SEPIC converter are it needs a large inductor and high voltage rating capacitors, as it gives a higher voltage conversion ratio. So, we need and also higher current stress on active switches as well as on diodes. Okay. So, this is the two topologies, these are the two topologies which are used, but having these disadvantages. So, the most commonly used and simple configuration having the advantages is the half bridge topology, which use a single leg, okay, single leg, and the number of passive elements are less compared to the Chuk and SEPIC converters. Okay. So, that is the advantage we are seeing here, and here for this converter I will talk about the its operation first, then how to design the filter components for this converter, okay, and then its controller used to have means if you are operating in a closed loop control system, then how to design the controller for it. Then I will see the simulation of this non isolated bidirectional converter NBDC, NIBDC or NBDC, in different names it is you are using in short forms. Okay. So, if you will see two switches here, one is the upper switch and you can say it as a lower switch. You can check properly, there may be some mismatch in the naming, you can adjust it, but it is all the same. So, top switch, bottom switch also you can say. Okay. So, it can operate. So, here as it is operating between the DC microgrid and the energy storage. So, it is operating bidirectionally, that means, when there is a excess power or excess generation, then the battery will charge, means it takes energy, and when there is a deficit generation, it delivers, the energy storage delivers. So, based on that, either it will operate in a boost mode or buck mode. So, based on that also this bidirectional converter is also called bidirectional buck boost converter also. Okay. So, this topology how it is operating, that will see, and with that single leg, if we will add more legs. So, to get some more advantages for some high power applications, we are going for two more topologies, that is called, one is a cascaded half bridge converter topology CHB, and this one, the second one is the interleaved bidirectional converter topology. Here only two legs are shown, only two legs are shown. This there can be multi-phase depending on your current requirement. Suppose you are going for a 100 ampere application. So, you can go on adding more number of phases, obviously more number of phases, more switches. So, complications or complexity is increasing, the control complexity, operation complexity. So, those are increasing, but the advantage is it will minimize the inductor current ripple, and also as current flowing through the, as you are dividing the current for this interleaved topology. So, the size of the inductor will also decrease. So, we can have a better modular structure. Okay. So, based on different applications, we can go for this interleaved topology or the cascaded H bridge topology. Okay. So, I have just given you the various topologies available in literature, but now we will focus on the simplest one, the converter having a single leg. Okay. The top switch and bottom switch, based on that I will talk about the how the means the operation of the bidirectional converter, how the converter is operating, when whether the energy is stored. Here I have reversed the direction, here this is the battery and this is the bus. Okay. In between we are using this bidirectional converter. Okay. So, the load is, the DC load is connected to the DC bus. So, this it is having the filter components, you have the input capacitor and output capacitor filter and inductor filter. So, you have to, after understanding the operation of it, we will try to do the design of the filter circuit first, means the converter design, when we will say means the designing the filter circuit for this converter. Okay. So, first let us give me means it is operating bidirectionally I told. Okay. So, in case of boost mode means the it is operating in discharging, means battery discharging mode. Okay. So, which switch is active in this case, and we have two active switches SB1 and SB2, okay, and the corresponding body diodes DB1 and DB2. Okay. So, when the switch for the boost mode, this SB1 is operated. Okay. I will show you in this in a better way here. Here if you will see the bidirectional converter during boost mode of operation, okay, and this is the equivalent circuit when switch this SB1 is on. Okay. So, during the on period of when the switch SB1 is on, so this is the path, means so inductor stores energy, okay, and the diodes DB1 and DB2 are off and switch SB2 is also off. But the how the, so here VDC it is connected to the load is connected here. So, at that time this capacitor supplies to the discharges to supply to the load. Okay. So, inductor stores energy during this, means when the switch SB1 is on. Okay. And in this case, to calculate the filter inductor, so we will use the volt second balance technique. By using the volt second balance technique, you can see the voltage across the inductor, let it be VLB. VLB, the switch is on. Okay. So, what is the equation? The voltage across the inductor is equal to the battery voltage. Okay. And what is the voltage across inductor? It is L di by dt. So, using that you can do this LB into di is the del IB, the current ripple, and the dt is the on time of the switch into the time period. So, using that you can find out the corresponding inductance value or the filter inductor of this bidirectional converter operating in while during the Busch mode. Okay. So, this is, you can try, this is the standard one. So, for other filter components also you can find out. For the capacitors you can use the what is required to calculate capacitor, that is the ampere second balance technique you can use to calculate the input and output capacitances during buck mode or Busch mode, that we will see. So, this is about the Busch mode, means when switch is on, but when the switch is off, in the next slide I have tried to show the Busch mode of operation means battery discharging, but the SB1 is turned off. So, at that time, so here actually basically in the previous case you can see the potential of this, means power means the switch is on. Okay. And here in the after you are turning off the switch SB1, so the this switch is on off, SB1 is off, and you have not given pulse to SB2. Okay. And DB2 is also not conducting. So, where the inductor is storing charge and suddenly you cannot break this current. So, what will happen? Now, current will flow from the means the current stored in the inductor will now discharge through this body diode of the upper switch. Okay. So, that is the battery discharging, means it is now supplying to the load. Okay. Switch is off, means all the three components SB1, SB2, DB2 are off and DB1 is on. So, like in this similar way you can do the analysis for the buck, means just reverse direction power flow, means I am just so here I have shown in detail. Again you can draw the corresponding circuit for to, so the means buck mode of operation when the upper switch will be operating and the lower switch is off. So, in the Busch mode the lower switch is operating and the upper switch is completely off, and so it is in the, when the switch is on it is conducting, means inductor stores energy, and when the switch is off it is flowing through the upper switch body diode. And but reverse is the case when we are going for the buck mode, that is the battery charging operation, means from the power will come flow from. So, here do not go by this, means this switch will be on and this will be kept off. So, when this switch is on, so it will flow in this way. So, inductor will store energy in the reverse direction. So, that is the battery charging mode, and when this switch SB2 will be turned off, the opposite will happen, means it will flow through the DB2. So, that is the buck mode or the battery charging mode operation. So, first one I have told boost mode or battery discharging, and so similar way you can draw the its equivalent circuit and do the analysis, and finally you can find out the corresponding filter capacitor components. So, now this is about the circuit operation, and now coming to the controller that is being used for this bidirectional converter. So, we are operating in two modes, already told, buck mode and Busch mode. So, based on that we can have we can generate the duty cycle so separately. So, that is called the separate controller approach. Okay. Separate controller approach means here from the we have the controller circuit. So, where the power management will generate the reference currents, and the reference current command will again further give the generate the duty cycle to means buck mode means battery charging, it is flowing in this way, and the boost mode means battery discharging, it is flowing in this way. So, it will generate the duty cycle for the upper and lower switches separately. So, that is why it is a separate control approach, which is normally we are going for going to use this what is called unified control approach, okay, where the controller I will while I will come to the controller I will show you the what is the control approach. So, here the controller will generate the duty cycle means when the upper switch is on, it will upper switch is on means which mode, buck mode, lower switch. So, it will give a pulse at that time, the inverted pulse will be generated or given to the lower switch, means when this is on means they will operate in a complementary fashion. Okay. So, that is generated by this unified controller, and what is there in the unified controller, that we will see. So, now coming to the bidirectional converter. So, after this again we will go back to the converter, but before sorry controller. So, before going to the controller design and its simulation, we will see the design of the filter components. Already I have told what to means from the different operating modes, means whether it is a buck mode or boost mode, you can get the corresponding inductance and the filter inductance, filter capacitance, input capacitance and output capacitance value. So, let us design for taking a power rating of 1 kilowatt. Okay. So, the load it is your based on the load actually we are deciding the power rating of the DC microgrid. So, and we are fixing the switching frequency, let us take it as a 10 kilohertz, you can go for 20 kilohertz also. So, and we are fixing the battery, we are choosing the battery voltage, and here for the DC bus of 48 volt where I am saying it as a normally LVDC microgrid. So, we have chosen a battery of input voltage of 24 volt, okay, and already I have told the output voltage is 48. So, as the power rating of the load is fixed, the output voltage and input voltage, this is the battery voltage and this is the bus voltage. Okay. So, the battery current, the maximum battery current can be we can get by the load power divided by the battery voltage. So, the maximum battery current it has to be designed is 41.66 ampere, this is 1 kilowatt load divided by 24 volt, and the output current when I will get the that is the output voltage is fixed to 48 volt. So, the output current we are getting nearly 21 ampere, 28.83, you can check it. And so, we have to fix the battery ripple current. So, this ripple current we can be considered between 10 to 30%. Here in this example, I have chosen 10% okay, of the maximum converter current of the input side. So, battery current we have calculated 41.66. So, 10% of which the ripple current of the battery. So, that is 0.1 of the 41.66 is 4.166 ampere. Okay. And the battery voltage, if you will see the battery voltage ripple can be also designed for 1 to 2%, okay. And for this example, I have chosen the battery voltage del V as 1%. So, based on that the input voltage ripple is fixed to 0.24 volt and the output voltage ripple is fixed to 0.48 volt. Okay. So, this is the we have calculated the maximum input current, the load current, the input current ripple and the input and output voltage ripples. So, now we have to find out this LB, the filter inductor and the filter capacitance values input side and output side one by one. So, this is already in this while discussing about the operating modes, I have shown you the This is the standard one, any reference you can follow to find out this filter inductance and using the volt second balance technique. And here, as all the values are known to us, the switching frequency is 10 kilohertz. So, this is the filter inductance is found to be 0.288, means nearly 0.3 millihenry. Okay. If you put the values, you can cross check the calculation, okay. And already using this del I, 10% of the maximum current rating. And to calculate the input side capacitance CB, it is required to find out the voltage, take the voltage ripple of the that is during the charging of the battery. So, charging of the battery means during the buck mode of operation, okay. And using that ampere second balance, you can calculate the capacitance, that is found to be 200. Just put the this formulas are given here, del IB into Ts divided by 8 into del Vb. Del Vb we have calculated 10%, sorry 1% of Vb. So, this is 0.24, and if you put all the values, this switching frequency is 10 kilohertz. So, we are getting a capacitance, input capacitance value is 217 microfarad. Correspondingly, for the when we are calculating the output capacitance value, we can do it by during the battery discharging mode, and this is the corresponding formula, and the output capacitance value is calculated to be 2170 microfarad, nearly 2200. The standard capacitance in market we are getting 2200 microfarad. Okay. So, this is the all the filter parameters we have calculated. So, I will give one assignment on it. Similar way, means I will just the battery voltage will change, switching frequency will change, and you have to calculate all the filter parameters. So, then now you can operate this converter in open loop mode also, means you can give a switching pulse, okay, of any duty ratio, but what is required? We have to regulate this DC bus voltage. Okay. So, for that we need the closed loop operation is very much required, and directly I am going to the closed loop, means using this dual loop control strategy. You can have a single loop also, only using the voltage control loop, but directly what we are using the final result I am showing you, which will give a better performance. So, here the dual loop means we have a outer voltage control loop, inner current control loop. Okay. The outer voltage control loop generates the battery current reference command, okay. And when it is compared with the actual battery measured current and given to the PI controller, it generates a duty cycle. Actually, this will be to limit the duty cycle. The duty cycle, the practical limit will be between the you cannot vary from, though we are saying that duty cycle can be varied from 0 to 100% or 0 to 1, but practically it is better to use between 0.1 or 0.2 to 0.8 or practical use 0.9 value, means 10% to 90% or 80 to 20% to 80% of the. So, here we are putting a limiter here, and I have missed one thing here, the current limiter also. Sorry, this is the current limiter, and this will the output will give you the duty ratio, which will be given to the PWM generator, and here we will set the switching frequency of this PWM, and it will give two pulses, means one actual pulse which will go to the SB1, okay, load switch, and the other one for the unified control approach. For unified control approach, it is inverted and given to the upper switch. Okay. So, this controller design and the PI controller tuning is the important factor before going for the simulation. Okay. So, how to design the PI controller, these are also very standard stuffs. Okay. Using the small signal modeling analysis, you can find out the control to inductor current transfer function and inductor current to output voltage transfer functions, and using the Bode plot analysis, you can fix the phase margin to 60 degree, and the here between this I forgot to tell one thing, the current loop between these two loops, which one is faster? The inner current loop is much faster compared to the outer voltage loop. So, first we will find out the bandwidth of the current loop and corresponding PI values. Okay. Then we will design the PI values for the outer voltage loop. So, the phase margin for both the loops are fixed to 60 degree, okay, to have a stable operation, and the bandwidth of the current loop is, as the switching frequency is taken as 10 kilohertz, it is 1/10 of it. So, we are fixing the bandwidth to be of the current control loop, which is faster compared to the voltage control loop, is 1 kilohertz. So, as fixing this, for the outer voltage loop, the bandwidth is almost 1/10 slower. So, the bandwidth of the voltage control loop is fixed to be 1 kilohertz by 10, so it is 100 hertz. Okay. So, using this and after doing the some tuning for the parameters KPKI parameters for the outer voltage loop and inner current loop is found to be this. So, Kp for the inner current loop is 2.3, and we will use these parameters to do our simulation. So, this is about the first part, means when we have designed the converter and we are trying to putting all these values, we will do the simulation. So, here the battery voltage we have fixed to 24 volts. So, market available battery is 12. So, we are using 2 lead acid batteries, means in our use we have actually taken 12 volt 2 lead acid batteries which are connected in series. Then inductor we have calculated 0.2 something here, 0.288, nearly 0.3. So, standard we have little higher value we have chosen 0.5 millihenry, and the nearly 50 ampere current rating, but the highest current rating is 41.6 and the input capacitance is 220 volt, sorry 220 microfarad, and this is 100 volt you can choose, and the output capacitance 200, standard is 200 or 250, okay, 250 volt, and the output capacitance is 2200, we have 2100 something. So, we have chosen the standard output capacitance that is available in market, that is 2200 microfarad, okay, and same 250 volt also. If it is not available, then you can go for this 450 volt capacitance also, and switching frequency again it is 10 kilohertz. So, we have to use the switching pulse of 10 kilohertz frequency. So, all these values will be used to do the simulation. So, going for here just I will show the simulation steps. So, which are now means already known to you. So, how to start create a model, then you have to create a new model following these steps. Okay. In the I think most of you are acquainted with Simulink, MATLAB Simulink. Those who does not know this, they can use this steps to make their new models. Okay. Then in the second stage you can add the blocks. The blocks are, we need battery, we need inductor, we need capacitors, all the components I will show in the next slide. Then you have to connect the blocks, okay. Then configure the parameters, like means you are dragging the suppose battery, the battery whatever will be available, suppose 12 volt, but as we need not connect two 12 volt batteries in series directly in simulation, you can put the battery parameter as 24 volt. Okay. Then you can run the model to run your means completely see your simulation. So, what are the specific blocks you need for doing this simulation? Here the sources means for this application we are going for this battery, Okay. You can get it from Simscape going to the electrical, then specialized power system, and inside the sources you will be getting this, means this battery or fuel cell, all the sources, but here for this simulation we are using battery. Okay. And that too lead acid battery or lithium ion battery, that you can select from the going inside the battery. Okay. Which one you want to use. The switches, you can choose MOSFET, IGBT. Okay. So, that is available also going through the power electronics components. Okay. Then all the filter components and the load, the resistor, inductor and capacitors are the loads that you will get inside the passive components, means Simscape, electrical and specialized power systems. Under that the passive components you will be getting this. Okay. And these are this slide I will share, you can see all the components how to get it. Okay. And for the voltage and current measurement you will use the sensor measurement blocks, and for scopes you can use the inside the Simulink or commonly used blocks, you can get the scopes. Okay. So, you will drag all the components and you can put it in your newly framed the model MDL you have created. Okay. So, you will drag all the components, battery, then you will double click on each one of the component to fix the values to it. So, we are using suppose 42 Ah battery and voltage is 24 volt. Okay. And the switch is here, IGBT is used as the switch, the RLC components, the filter components, the inductor and the input capacitor, output capacitor components, and this is the voltage and current measurement unit which will show you the measured currents. Okay. And this is the display, the simulation, means you can see the results through the scope, and this is here it will display the values. Okay. And if you want to merge the data you means the signals you want to see, you can use the bus selector to see it. And this is the breaker to, if here in this model we are using to switch on and switch it off to change the loads. Okay. So, this is after following those steps you can make your model which looks like this. Okay. Here the scope is connected which is showing the all battery parameters, SOC, the voltage and current of the battery. This is the current of the inductor current for which you are connected another scope here. Okay. And this is the switches you have used to connect and disconnect the loads, that is not actual switches. So, the BDC is formed using these two IGBTs. Okay. The bidirectional converter actually uses, this is the one leg, but do not get confused, these are the switches to make the load on and off. If you are increasing the load or you are disconnecting the load by changing this pulses, through the pulses you can have it. And here you can put another scope to see the your output voltage, the dislink voltage here. Okay. So, again the same thing. So, here this is the open loop system, you can say, means here there is no control system, means I have not put any control. You can put if you want to operate in a open loop mode, you can put the get pulses and then you put a inverter, give it to the lower leg. So, you can operate the bidirectional converter in open loop mode, but for the closed loop operation having the two dual means the two loops, that is the outer voltage loop and inner current loop. Okay. So, here the outer voltage loop, the voltage reference is fixed to 48 volt and the Kp Ki values we have already designed or tuned it. Okay. Here I have shown those parameters will be used for this doing this simulation. Okay. Then you can, after completing this means changing this Pi values, okay, you can run this. First you will set the battery voltage and you are fixing the load, and for the again the whole system is again you are doing for the with the load change condition also. Okay. Final output pulse which is given to turn on and turn off the both the switches of the bidirectional converter. So, you can run the simulation by pressing this run command. Okay. And you can see this is the final. So, this model I will share shortly and you can run it. In case of any problem we can see it in the tomorrow's class, because today I do not think now if you have any doubt we can discuss, but simulations you could take your time and run it, and after that tomorrow's lab demonstration you can discuss about the any problem in case of if you are facing any problem in doing the simulations. Okay. So, these are the results. So, here I have means this is done for the means the load power is varied. Here the load is from 600 volt to 800 volt, sorry 800 watt, 600 watt to 800 watt, then again it is changed to 500 watt. Okay. So, by switching on those here you are switching on, you are giving pulses to these switches to make the resistances means get connected to the circuit. Okay. So, you are varying the load in this way. So, first is the you are fixing the regulating the DC bus voltage. Okay. So, DC bus voltage is fixed at 48 volt. Okay. So, here there is a increase in load. So, there is a voltage dip. When there is a decrease in load, there is a voltage swell, means there is sudden increase in voltage, then it is again tracking the, and this tracking time is very fast. You can the controller is tuned in such a way that it is very well regulating the bus voltage at 48 volt. Okay. And this is the DC bus voltage waveform, this is the corresponding load power waveform, and this is the inductor current waveform. Okay. Inductor current you can say it is the battery current. Okay. So, here we have not connected any source, only the battery with the grid, means so that is that so it is only operating in a discharging mode. So, discharging mode means so battery current is always positive. Okay. You can see the when the load is increasing, the correspondingly the battery or the inductor current is increasing, and again when the load is decreasing, it is decreasing, but it is always supplying. And these are the waveforms of the battery, that is SOC. Battery SOC initially we have fixed it to 80%. So, it is going on discharging. So, it clearly shows ki it is operating in a discharging mode, or that is booster buck, discharging boost mode of operation. And this is the battery voltage, and corresponding again here same thing is shown here, which is taken from this directly from this scope. Okay, for the battery parameters. Okay. So, this file I will share with you, and if you want to you can change the parameters, the loads, the switching frequency to see the variation. If you change the inductance value, what is the effect. So, the with the model also you can do the run means analyze the results, what is affecting what, means the if you are varying the inductance, if you are increasing the switching frequency, or up to what value you can vary. So, those things you can see easily by running the simulations. Okay. So, this is the assignment question, where I have changed the input battery voltage to 36 volt. Okay. Output voltage is same fixed to 8, and the ripple switching frequency is changed to 20 kilohertz. You can try it to find out the steady state duty cycle of the bidirectional converter, and the inductance when it is operating. Obviously, we have done all the analysis for continuous conduction mode. So, calculate the inductance, the input capacitance, and the output capacitance values you can calculate. Okay. In the similar way, already I have given all the formulas, and the way how to do it also I told. Okay. So, this is about our thing, means what we have done, means the tutorial content for this today's class. But I will tell little bit about tomorrow's thing, which we are going to implement in the lab, means already it is implemented, it will be demonstrated to you in tomorrow's lab class. So, overally what was in our topic, our aim is to integrate the renewable energy system to the DC microgrid, and here in the course we have mainly focused on the mini hydro power plants. Okay. So, when you are going for this the renewable energy source, whether it is a mini hydro or wind. Okay. So, already you have seen the output is AC. Okay. And if you are taking the sources like PV or fuel cell, the output will be DC. So, based on that step will be little different in the step. but here I have explained you the means I have tried to show you the design steps. So, first what you have to do, if you are going for a mini hydro or wind, it can be either way, means any energy source you are choosing. Okay. So, mini hydro design already you have learnt lot from such class. Okay. That was the main aim of this course. Okay. So, you have to choose the corresponding, after doing the power plant design, then coming for the electrical part, we have to choose the generator. Okay. So, generator, what can be the generator options also, that Professor Sarkar has already explained you, and for wind also there are synchronous generator or induction generators, you can go for it. Okay. Then you have to choose the suitable converter. So, here as the output for both these sources is AC. So, we have to go for AC to DC, and then depending on your bus voltage, those things, whether it will be means buck or boost operation, that will be decided. Okay. And for both the cases you have to go for, means after this AC to DC conversion, okay, there can be single stage directly AC to DC doing the MPPT, as well as means this can be in using a single converter AC to DC doing a MPPT operation, or you can have two stage, means AC to DC only rectification, then you can go for a DC to DC converter to do the MPP operation. So, how to do MPP, that is not this course content. So, but after doing this part, you have to maintain the output voltage constant. So, that is the DC bus voltage regulation. Okay. So, that is the in the lower control, lower level of control you are doing that. Then comes the in the upper level you are going for this power sharing and power management. Okay. So, these are the design steps when we are going to means connect any RES to a microgrid. Okay. So, that its implementation you will see in tomorrow's class. So, here just I have tried to show the what we have implemented in our lab, but having two sources, two energy sources and two storages, but tomorrow we will see about having a single source and single storage, means battery energy storage and PV as the source. Okay. So, here we will be going for this DC to DC converter, this will be the storage DC to DC converter. Okay. And here for the supercapacitor again we are going for this DC to DC, this BDC. Okay. So, it is this topology is called here also this bidirectional converter what I have discussed just now. So, here we are going for this active topology, active configuration you can say. There are other configurations also, semi active, passive, but we are not discussing about those things. So, here first you have to design and develop the each source. First we have in our lab we have designed the wind energy conversion system, we have chosen the generator, then the corresponding AC to DC rectification we have done, then DC to DC converter we have used, this is a buck converter we have used for the MPP operation, which is interfaced again connected to DC bus. Okay. And this, so as this is a doing MPP operation, this bus voltage is fluctuating. Okay. So, to keep the bus voltage fixed at 48 volt, we have designed for a 48 volt system, then we are interfacing with this battery energy storage system, battery with the BDC. Okay. So, these things will be implemented, means already implemented, it will be explained to you tomorrow. So, then after developing this wind battery system, then we have integrated the supercapacitor to it, making it a hybrid storage, and after that we have also added a PV system to it, making it hybrid source. Okay. Combined source means PV and wind having complementary characteristics, and battery and supercapacitor having complementary characteristics. This is already implemented, but in this course you will be only seeing the first part. Okay. Means this part, PV with battery. Then so in the low level of control we have tried to make the DC bus voltage constant. So, going to the upper level of control, higher level of control, where we are going for the power management, and the SOC estimation of the battery is also done. The overcharging, it is prevented from overcharging, discharging. Okay, for that we are the power management, the basic power equation is shown here for all type of sources. I have shown here 3 sources, but till now we have not added this one in our lab. Just as we have also done any source, number of sources, you can the total power, incoming power minus the losses occurring in the system should be equal to the load power plus or minus, means battery, when there is excess source power, battery will store, or okay, and when there is a deficit power, battery will supply. Okay, like that. This is the power management we have to implement. So, those things will be shown to you for a single system, and this is one photograph just I have shown for the PV as well as wind. So, here the ACIG based system is we have taken, okay, and PV, now this is for a very low power system we have designed initially, 200 watt within that operation, okay, and the corresponding converters and the sensor circuits, these are the converters, and the sensor circuits are also designed here, shown here. So, actually you can see in the lab tomorrow. Okay. So, this is the content. So, these are the references. Okay. If you have any question, you can ask. So, you can
Hello,
stop
ma'am.
here. Yes, tell me.
Yes, ma'am. What is if during the hardware implementation, the
Yeah.
control signals? What is the method followed for generating the control signals?
Method means platform you are talking about.
Yeah, platform. Yeah.
Means here we are showing means 2 will be showing tomorrow, means for this microgrid thing we will be showing dispatch based implementation, okay, and one DAB also we are going to show you the DAB demonstration. There this C2000 microcontroller will be implementing. Okay, for microgrid we have used actually this dispatch, and also polarity based another wind based system we have developed, but tomorrow's class will be showing about the dispatch based implementation.
Okay, ma'am. Thank you.
So, we can close today's session. So, thank you all.